Hello and welcome back. It's time to continue our video tutorial series on Chapter 10, Section 5, Testing Convergence at Endpoints. Today we'll go into Part 2, Comparison Tests. There's some pretty cool stuff in this video, but a lot of it is not on the AP content for this year, but it's pretty memorable, and I encourage you to listen to it anyway. In the previous video tutorial, we covered the integral test, which basically says that the integral from 1 to infinity of f of x and the sum from n equals 1 to infinity of f of n, which we usually call an, either both converge or both diverge. And we also talked about harmonic series and p-series, and basically that the integral from 1 to infinity of 1 over x to the p converges if and only if p is greater than 1. So that's pretty nice, but that's still a pretty limited set of things that we can do. With our new two tests that we'll get into today, it'll broaden our ability to determine convergence for a much larger number of series. The first of these is called the limit comparison test. So suppose we have two series, an and bn, both of which have to be positive, maybe not initially, but after some point n, some index n, from then on they're both positive. And we take the limit of an over bn. We have three cases. We either get some positive real number c, or we get 0, or we get infinity. Now, if you get a positive real number c for a limit, then either both of the series converge or both diverge. So that's pretty useful. If the limit's 0 and the denominator sequence converges, the top obviously has to be smaller, so the top converges. Similarly, if limit of an over bn is infinite and the bottom diverges, then the top has to be larger, so it has to diverge. Now, to be honest, most of the time we use the first case of this, that if the limit is some fixed positive real number, they either both converge or both diverge. So let's take a look at some examples of this. Which of these series converge and which diverge? So let's start off with the very first series. So this is a series, and each of the terms in it is growing in such a way that the top is growing linearly and the bottom is growing quadratically. And if we kind of strip it down and look at leading terms, the leading terms are 2n over n squared, which is like 2 over n. So that's the series that I'm going to compare it to. Actually, I'm just going to let bn be 1 over n, which is good enough, and you'll see how it works out. Now I've got it to the limit as n approaches infinity of 2n squared plus n over n squared plus 2n plus 1, and I could do this a variety of different ways. I could use L'Hopital's rule, but the simplest way is when you have one polynomial over another and they have the same degree, the limit is just the ratio of the leading coefficients. So in this case, I know that the two series, the one that they gave us and 1 over n, either both converge or both diverge. So let's look at the one we made up. Well, that's just 1 plus a half plus a third. That's the harmonic series. And we know the harmonic series diverges. So the original series A must also diverge because the limit of the original series over the harmonic series is 2, and by the limit comparison test, if the limit of the ratio an over bn is a real number, they either both converge or both diverge. So that series diverges. Let's take a look at the second one. The second series is a little bit different. This is very, very much like this series 1 over 2 to the n, so that's the one I'm going to compare it with. At this point, it should be pretty obvious that the limit's going to be 1, and if you don't see that, just divide the entire top and bottom through by 2 to the n. So this series and 1 over 2 to the n either both diverge or both converge. And if we take a look at that's just sum from n equals 1 to infinity of 1/2 to the n, and that converges because it's a geometric series with a ratio of 1/2. I hope that makes sense. So basically, so far we have that the first series diverges, the second converges. What about the third series? If we use the same approach we used in example 3a, we see that this functions a lot like 3n over n cubed, which is a lot like 3 over n squared, so I'm going to compare it to 1 over n squared. It's worth pointing out that in this series we don't start at 1, here we start at 2, that doesn't matter. Basically it's some initial point out to infinity, and so I'm going to let an be the term of this series, and I'm going to let bn be 1 over n squared. So now if we take a look at the limit as n approaches infinity of an over bn, we get, and again, when you have a rational function, or a rational expression in this case, like a polynomial over a polynomial, and the top and bottom have the same degree, limit as n approaches infinity of that is just the ratio of the leading coefficients. And so since I get some fixed real positive number, I know that the original series, that's 3c, and 1 over n squared, either both converge or both diverge. And what about sum, n equals 2 to infinity in this case, of 1 over n squared? Well, that converges by the p-test. So at this point we have diverge, converge, converge. Let's take a look at the last example. I hope you remember from the very, very beginning of the year that limit as h approaches 0 of sine h over h is 1. Well, in this case, I'm going to let h be 1 over n. So my sequence an is the sequence d they gave me, which is sine of 1 over n, and I'm letting bn be 1 over n. So then looking at the limit as n approaches infinity of an over bn is looking at sine 1 over n over 1 over n. And as n approaches infinity, 1 over n approaches 0. So this is limit as n approaches infinity of sine a very small thing over similar very small thing, which has a limit of 1. So in this case, either sine of 1 over n and 1 over n either both converge or they both diverge. Since we know that sum of n equals 1 to infinity of 1 over n is the harmonic series and it diverges, that implies that sum n equals 1 to infinity of sine 1 over n also diverges by the limit comparison test. So we wound up with diverge, converge, converge, diverge. And that's some good examples of the limit comparison test. Now we're going to talk once again about the alternating harmonic series. You remember the alternating harmonic series. It's 1 minus a half plus a third minus a fourth plus a fifth. And it did converge. It converged to the natural log of 2. And the reason was, if you'll remember, we start by going right 1, and we go left a half, right a third, left a fourth, right a fifth. And so it really feels like we're horning in on some specific number, just getting closer and closer to some specific value, because we're always trapped inside our long last leap, and our leaps get smaller and smaller and smaller. So here's the theorem, and we've seen it before, it's just a repeat. In my mind, they've expressed this a little awkwardly. They're saying, think of a sequence having the form, or a series having the form u1 minus u2 plus u3 minus u4, etc., where all of the u's are positive, so we're adding and subtracting positive things. And if you look at their absolute values, each term is larger, greater than or equal to the next term, which means that they're shrinking, and the limit of the nth term has to be 0. Well, if all of those are true, then the series converges. But I'm now going to remind you about some terminology. So a sequence like 1 minus a half plus a third minus a fourth plus ... does converge. We explained that. But on the other hand, if I look at the sequence of the absolute values, that doesn't converge. If it did, then we would have said the original series converges absolutely. But this is the harmonic series, and it diverges. This is the alternating harmonic series, and it, we say, converges conditionally. And what that means is, although it converges, if I look at the sum of the absolute values, that doesn't converge. And the little theorem to remind you some more about this, even though I think this is now the third time we've looked at it in the last 2 chapters. So this theorem, Theorem 13, the alternating series bound theorem, says if you have a series that meets all of the conditions we just talked about, the terms alternate in sign, their absolute values keep getting smaller and smaller with a limit of 0, then the truncation error, if you stop at the nth partial sum, will always be less than the first term you left off and has the same sign as the first term that you left off. So let's take a quick look at an example, although I know we've seen them before. Suppose I added up the first 99 terms, getting the 99th partial sum of the alternating harmonic series. We know that the alternating harmonic series converges to natural log of 2, but how much error do I incur if I stop at 1 over 99? Well, I know the error is less than 1/100th, and that the error is actually negative. So I know that the sum of these terms is actually no more than 1/100th larger than natural log of 2, because the first term I left off is negative, and so the actual answer is below my partial sum so far. I hope that makes this all clear. I know we've been over this quite a bit. Now for something really cool. Starts a little bit boring and tedious with some terminology. So remember what absolutely convergent series were? They didn't have to be all positive. They could be mixed, positive and negative. But if you take their absolute values, that series still converges. A series is absolutely convergent if the series that you form by taking the absolute values of the terms converges. So let's consider a very quick one. The series 1 minus a half plus a fourth minus an eighth plus a 16th, it meets all the requirements of the alternating series bound theorem, so we know that it's going to converge, but even more, it is a geometric series with a ratio of -1/2, so not only do we know it's going to converge, we know what to. It'll converge to a over 1 minus r, 1 over 1 minus -1/2, 1 over 3/2, 2/3. Now, if I look at the series formed by taking the absolute values, I get something totally different. In that case, I get 2. That's no surprise that all of a sudden the negative terms turning positive should make it add up to more. But this example is a series of, it is alternating signs, but it still converges absolutely. So the theorem says if a series converges absolutely, you can rearrange these terms all you want, and it's still always going to add up to 2/3. That shouldn't be surprising. Here's where the surprises come. This is just cool. If I have a series that only converges conditionally but not absolutely, then I can rearrange the terms to form a divergent series, or I can rearrange it to form a series that converges to any number I like. I know that's hard to believe, but I'm going to go ahead and explain it. So this is, in sigma notation, the alternating harmonic series. And I'm going to show how I can rearrange the terms in the order of addition to make it into a divergent series, and then into one that converges to pi. Right now, if I just add left to right, it adds up to the natural log of 2. So first, let's point out that we can split this series into two series, one all positive and one all negative. So I can split my alternating harmonic series into two series, 1 plus a third plus a fifth plus a seventh plus dot dot dot, and another negative a half minus a fourth minus a sixth minus an eighth, the negative terms. Now I want to point out that the first of these series, let's call it AN, will add up higher and higher and higher without bound. Should be pretty obvious that that's the case, but it does. That grows without bound, but very, very slowly. It heads towards positive infinity. The second one heads towards negative infinity. And no matter how many finite terms I pull off either AN or BN from the beginning, the tail of it will always add up to either positive infinity in the case of AN or negative infinity in the case of BN. So here is how I make a divergent series. I pull terms from the beginning of AN until it adds up to at least 1. Now I start pulling terms from BN and adding them until it adds up to negative 2. Now I go back and start pulling terms from AN until I'm adding up to positive 3. Now I pull up terms from BN until the total reached so far adds up to negative 4. I keep doing this forever, which I can do, and obviously that series will never converge. Now to make a series that converges to pi, I do something very similar. I pull terms from AN until the first total is above pi. Now I start adding in terms from BN until I drop below pi. Now I add terms in from AN until I'm above pi again. Now I add in terms from BN until I'm below pi again. As I do this, what's going to happen is I'm going to be above pi, then below pi, then above pi, then below pi, and I'll keep pulling terms off both AN and BN and getting closer and closer and closer to pi, so that series converges to pi. Isn't that pretty awesome? I can make the series add up to negative E or anything I want just by choosing the order in which I add the terms. Might take you a while to wrap your head around that, but it's true and it's awesome. So that's the end of 10.5, Part 2, comparison tests, also looking at rearranging conditionally convergent series and showing that you can make them add up to whatever you like or make them diverge, which is pretty awesome. We've got one more part and we'll be done with 10.5. I hope everyone is healthy. I hope everyone is staying well. I miss you guys. I really didn't expect the year to end this way. I hope you're all dealing with this new normality as well as you can. And I'll set up a chat on Tuesday, and I hope most of you come in and visit with me, and I'll send out an alert about that. All right, bye-bye.